So with this presentation, I'm going to, there's a lot of pictures in it, so hopefully it's not going to be too taxing. And so I want to show you a little bit about a bit of scenery in Tasmania, and a bit about how salmon is grown in Tasmania. And for those of you with a selective breeding bent, I'll also be talking about how we do the finfish breeding, or the salmon breeding in Tassie. And I mean, it's, the way we do the salmon breeding is a little bit different from the way it's done in the rest of the world, but largely it's pretty much I suppose a kind of a case study on how finfish selective breeding is done. So, this is Tasmania. This is I think it's the line of 40 degrees latitude, runs kind of through the middle of Tasmania. So in terms of salmon habitat, we're at the very extreme end. So I'm not aware of any other grower elsewhere that's growing at such low latitudes. So what it does mean is that we've got a warmer climate, we've got warmer water temperatures, and that brings with it its own set of problems, which I'll talk about. But it's obviously an introduced species. So our population came from Canada originally. I think it's at the Phillip River or somewhere, if you know Canada. So one small population. So it came from Canada to New South Wales, which is up here, and it was held in a fisheries institute for a long time. In the mid-80s, the Tasmanian government decided that they wanted a salmon industry, and so they were moved down to Tasmania, and that became the start of what I call the Tasmanian land race. And in terms of a government decision to start a new industry sector, it's been remarkably successful. And I think there's probably many case studies where there's not that sort of success, but it has grown to be now Australia's most valuable seafood sector. So there was wild fisheries sectors that were more valuable, so that the salmon now exceeds that. And there's some stats there on the size of the industry. Although it's big for Australia, it's only about 2% of the world's salmon production, so it's tiny, and it's a domestic market. So there are big corporates are involved in it. So there's one big public company and one public company and one very big private company. And so you're talking of millions and millions of dollars investment. And so what I'm going to do now is talk you through the production system. So just in case you didn't know, the salmon has a freshwater spawning, so it spends about 1 year of its life in the freshwater hatchery, and then it's transferred to the marine environment. This is down this bottom end of Tassie here is the main growing area, and it typically grows out for 1.5 years in the marine environment. So this is a shot of the hatchery. So this is about probably 80 kilometres from Hobart, where I'm based. It's probably it's 100 kilometres, so it's probably about 150 miles from the salmon growing areas. So this was sited because there's fresh water in the river there, and that's the source of the water for the hatchery. This hatchery would probably produce around 2 million smolt a year. It's sort of changing a bit now though, because with the selective breeding program, it's become really the source of eggs and broodstock. So they'll be selling eggs to other hatcheries. This is eyed eggs, fertilised eggs. These are the eggs in the trays. This is the egg. So these are the eggs that have been fertilised, so they just bundle them up and they send them to these other hatcheries, and they put them into these sorts of trays, and they'll grow them out, and they grow into smolt. So this is some shots of where the sort of environment where the salmon are grown. So it's largely estuaries. Should have a better map, but the coast of southeastern Tasmania is a bit like the coast around here, except maybe not quite as complicated. but it's a sheltered coast, a lot of estuaries, a lot of sheltered waterways. And so there's these lease areas in here where there would be salmon cages, and often these leases go with a shore base, so boats and stuff, all sorts of activity to go out and support those. So these are the commercial pens, and I can't do a good comparison, but they're about probably 40 metres in diameter. This is a bit smaller. So this one here, so this shot was taken because that's the pen we use for our selective breeding. So every year we have to send a group of fish out there to do our measurements and our performance test, and so we've got a purpose-built pen to do that. So you've got to think of Contra Seasons for us. So spawning is in the winter. So I'm always up at that hatchery, which is a cold place in the depths of the winter. And so May you can really put a date on your calendar. So May is spawning time, and they have a full 12 months in the hatchery. And so about spawning time next year, you have these fleets of trucks travelling down the highway taking the salmon down to the sea. And I can't remember how many go into each of those tanks, but it sounds a lot, but there's many truck trips required to take them down. And so when they get them down to the area, so this is now unloading in the marine site, they just simply pump the smolt out. So when I say smolt, we're talking of 100 gram animals. They're about this long, and they just go down the pipe and into the pen. And judging by this pen, I think this would be our purpose-built selective breeding pen. So that's not a commercial pen. So this is a shot of just how the pens look when they're out at sea. So this is a channel area. So it's a fully marine site. There'd be occasionally you get these channels of fresh water running through it, but it's mostly a marine site. And so within a lease you might have I don't know, maybe 6 or 10 of these cages. And you'll notice that they're draped with all sorts of things. So that's a bird net over the top. So these are 40 metres. They'll hang down into the water, probably 20 metres, and so that'll be the fish net. And outside the fish net, you've got these big predator nets, because one of the major issues is seals. And seals are smart, aggressive, and they cause the salmon growers heaps of angst. And we had a seal that got into our pen one day. This is our pen of our breeding fish, and he wasn't in there very long, but when we came back to do the next measurement, there were probably 30 or 40 fish that we didn't find, and these were fish this big. So this shot here is showing the a feed silo. So one way of feeding the fish in a commercial pen is to have a feed boat going around and some guy just squirting feed into it. But increasingly the companies want to do this more automated system. So you can get a height so that there's probably maybe 3 times that height is the depth in the water, so that's just full of the feed. And the feed is pumped out on those pipes. So I thought I had a shot, but anyway, so it's that's the one. So you're probably within sort of a 200 metre radius, you'd see these big commercial pens around, and the feed is somehow, must be some sort of air pump, I think, which is pumped into the pens, and you have a guy sitting in the station. It's all high tech, and he would be watching as they're feeding, and the feeding might go on for maybe 10 or 15 minutes, and he's waiting to see that when fish stop feeding. And so when the fish stop feeding, when they stop taking the pellets, then he'll turn it off. And there's So on the old feed boat system, there might have been maybe 1 or 2 feeds a day. He's probably doing 4 or 5 feeds a day. And from a salmon grower's point of view, the salmon farmer, the farm manager on this site was telling me how the capital of that big silo, he said, paid for itself in about 18 months, because this was such a better feeding system. It was more efficient. And he said on the old feed boat system, if someone's had a bad night, if they've had a hangover, they might feed the fish or they might not. And but he said with this system, they're fed every day, they're fed the right amount, and when a salmon is not being fed, it's not growing. So I mentioned that Tasmania was at the climate extreme for Atlantic salmon. So one of the major challenges, and this was what the major challenge given to the breeding program, was to do something about that disease. I think that was do something about the salmon disease problem in your terminology. So it's a disease called amoebic gill disease. So the amoeba are free living in the water column. They're just a naturally occurring thing, and they're a parasite on the gills. And you probably can't see it very well there, but there's the symptoms are these white lesions, and you also get lots of mucus produced. Someone described it to me once as it's like an asthmatic reaction of the fish. It's and if they're not treated, then they die. And during the summer, you're probably the treatment is they have to bathe them in fresh water, and I've got some shots of that. But during the summer months, they're bathing probably every 30 or 40 days. In the production cycle, a commercial salmon might get at least 10, 12 commercial baths. And the salmon growers say to us that the difference between the salmon, the cost of production in Europe and Tasmania, is about $1.40 per kilogram, and that $1.40 represents the cost of this disease. So it's a massive impost on the disease, on the industry. So this would be assessing in our breeding program, but routinely the farm hands, the technical hands on the farm, would be inspecting the fish like that. They'd take a sample of probably about 40 fish, they'd look at the gills, and they'd monitor the progression of the disease. And they would be doing this at probably every 2-week intervals in the commercial pens, so they're constantly moving around all the pens. And this guy, Dave, was saying that if they don't keep up, then they get an absolute caning, or if they get really behind and fish start dying, then he said it's the sack. And it's just such a critical issue for them. And so here's some shots, not very good ones, of this commercial bathing. And I think if you had an engineering event, you just marvel at the way this is done. Because it's just imagine the commercial pen, they put a liner in it, and then they fill it up with fresh water. So you've got to have a supply of fresh water, which in Australia in droughts is a pretty major issue. So the pen hangs into the water about 25 metres, so this plastic liner would probably fill up with about 10 metres of water, and then they literally pump the fish from one pen into this other pen, which has got a big bath of fresh water. Not a very good picture, but you can see some salmon flying through the air. They're being pumped into the fresh water. So they would sit in that fresh water for probably 2.5 hours, and then the farm hands would pull the liner away, and so that just disperses, probably spreads inoculum everywhere, but that's enough to break the disease cycle of the fish. So that's the end of my slides on the production. So what I'm going to talk to you now about is our selective breeding program. And so This started in 2004, so in terms of other salmon programs around the world, this was a late starter. So the industry took them a long time to get around to it, to get their act together. But when they did start, this was really the brief they gave us. They wanted to reduce the effects of AGD. There'd been probably 10 or 15 years of research on looking at husbandry ways to do it, and when we were starting this, I remember one of the guys saying, he said, look, we spent all this money on AGD research, mealy gill disease research, and he said, we haven't got anything other than what we were doing, which is bathing in fresh water. And incidentally, they discovered about bathing in fresh water because back in early days when they were towing fish around, they towed some fish through a sort of a brackish of freshwater flow, and the disease disappeared. So it was sort of a fortuitous thing anyway. But anyway, so that's our main breeding objective. This is the other main objective, which is to reduce the grow-out time. And these I've numbered with the 2 because the secondary objectives to reduce the incidence of early maturation and maintain product quality. So what they're really saying there is that they don't want us to make it any worse by what we're doing and selecting from these other traits. And this early maturation, this is another issue which is uniquely, well not uniquely, it's more apparent in Tasmania, so more apparent at our higher water temperatures. And what happens is that you get more fish, particularly males, that mature before their harvest size. So the aim is in this 18-month marine grow-out to grow them from this 100-gram animal to about a 4.5 kilo animal, whatever that is in pounds. But they really do grow quickly in that period. But they also, there's a proportion of the population that matures early. So they would mature probably after their first summer, which is probably after about 7 or 8 months in the water, in the marine environment. And at that point they really stop growing. So all the fat, the astaxanthin, the colour, goes into their sexual maturation, and they just become an unmarketable fish. They also become a fish that's very prone to mealy gill disease. So that's, I think that'll become another major issue for the breeding program. So here's just some rough costs of what they spend. So in total, that's about a $1.5 million program, $1 program. That's what it really costs to run a salmon program in Tassie. Those CSIRO costs are a little bit old now, but I think I prepared this for a CSIRO talk, so that's why they're there.
The revenue sources?
So this is, so when we did this program, CSIRO was spending the sum of that amount, so we were kicking in that amount, and the industry were paying us that amount directly because I suppose our that was their contribution to our program. So this is the breeding cycle for a salmon. I haven't got it. So 3-year cycle, 1 year in a hatchery, so we've seen the smolt trucks going out. And for biosecurity reasons, there's the broodstock need to remain in the freshwater in the hatchery. So we can't take our marine tested animals back to the hatchery to use as breeders. So we have this marine progeny test which comes to a halt there, so that's our information gathering stage. But we also keep a bunch of their brothers and sisters in the hatchery as potential broodstock, and they're the ones that go around to complete the breeding cycle. So this is the cycle for, I'll just go back. So here's the main areas of activity. So I've got some slides that I'll just step you through each of those. So 4 main areas of activity, which is spawning, tagging, and I'll explain the DNA bit, measurements through here, and then we do the genetic evaluation and selection. So that's the cycle that happens for 1 year class. So, but we actually have 3 year classes in the water at any one time. So if you can imagine 3 of these rings, and they're all slightly offset, so there's a whole heap of activities, a whole heap of field activities that are always going on. So what I'm going to do now is just to step you through each of these 4 main areas of activity, just to give you some sense into how that breeding program works. So the first thing is the spawning. So I mentioned this happens, it's a winter time activity, so this happens in May every year. So that's roughly what we do. We've got 90 males, 90 females. Every parent gets crossed twice, so that means we've got 180 families. And this is the activity on spawning day. So this guy is holding a fish. Harry here is squeezing the milk out of the fish, and it goes into a bottle, which is here. But, so that they get numbered. We've got a crossing design, different story, on some computer software we developed. So this identifies the cross. And so later in that same day we would strip the eggs out of the females. They go into a bucket, and from our computer we would find the number of the milk bottle, and the milk gets poured in, and that's fertilisation. So it would sit, that egg bucket, it's just a bucket about that size, it would probably given I think it's about 20 minutes for the fertilisation, and then it's washed off, and then it's put into the those incubating trays. If you think back to that slide of all those trays in the hatchery, that's where they incubate. So we have a point of difference here with what many other salmon breeders would do, in that they would do this fertilisation, and then they would have say maybe 150 controlled environment tanks where those animals are reared, and when they're big enough to tag, and they can tag them at about 30 grams, they would take them out, tag them, and put them into a common environment. And to do that, they have these very expensive systems. So to keep conditions the same in that early environment, they're high-tech. They have to be computer controlled, they have to be fed the right amount, they have to be the same temperature. But our industry decided that they didn't want to spend that amount of money on that sort of system, so we've gone for a DNA fingerprinting approach. So after the eggs are right up, as they say, so when you can see what's a viable egg, we would count out a set number of eggs from each of those hatching trays and put them in, and then they will hatch into a common environment. And that's what that means. Combined families after, well, actually it's before hatching, and then we would grow in fresh water for 1 year until they're a size of that animal there. So now we're now 12 months later, so we're now in June the next year, so we're still in the depths of winter, and we're still in the hatchery. And so what we're doing now is we're going to electronically tag, so we do about 7,500 fish, and at the time, I've got some pictures here, so this is the tagging. Some of you probably know pit tags. This is the passive integrated transponder tag. So this is about the size of a grain of rice. We don't use this gun anymore, we just insert them in with a scalpel. But back in the old days, this is what we do. We just put the tag into the fish, and in a day, crew would be doing probably at least 1,000, maybe 1,500 fish a day. But at the same, so after we tag it, we would then take a biopsy, here a fin clip, put it into a tube. We would already have the DNA of the parents. We've got the DNA of the progeny, and we can use a panel of microsatellite markers to determine the parentage of this animal here, or the parentage of the tag that goes with the animal there. And that's a contract service that we've had done by a company in the UK. It's costing us £8 only. What's that? £8 or £9?
What, $6?
It's more than that. Yeah, I think it's about $15.
Oh, sorry, I was going the other way down.
Yeah.
So it should be doubling up.
Yeah. So, sounds a lot. So this is a big cost item of our program. So over $100,000 would be spent on this part of it, but that's considered cheaper than building and maintaining a separate hatchery system to raise families. Okay, so this is the tag reader. So fish has got a tag. This is a tag reader when it was brand new. It doesn't look anything like that now. And so we would have that. It would log to a computer, and also can't show it, but we've got a balance at the time we're measuring it. We've got a barcode reader to measure the tube number, and so we just log everything to the computer. So we got a system that's paper-free. So, thinking back to the diagram, we're now up to the third point, which is doing our main measurements. And so the purpose is obviously to get our information so we can make our genetic selections. So we do measures of the marine fish. So after tagging, we've transferred half of our fish to the pen. Think back to that pen I showed you. And another half stay in fresh water. So we do measurements on both. We get good information from both. So lots of data, and this is the sort of thing we're doing. The electronic length board, and this is the gill scoring. So this is to measure the AGD. So we found that by just doing a visual assessment of the spots on the gills, that's been a very good indicator of the disease resistance. And in our pen here in our marine environment, we would get probably at least three. We have had up to 5 infections in a summer. And so we would measure, our aim for the breeding program is to measure these gill scores at every infection. And we also measure some of the traits in the freshwater. So what the growers obviously want is a fish that grows well in the marine environment, but there is a correlation between freshwater performance and marine performance. So there is value in doing these freshwater measurements. But of course the main measurements are done from the marine animals. I'll come back and I'll show you got some better pictures of this. So our main measurements are done at harvest. So this would be, so our normal harvest measure is done in, say, October. So that would be, that's sort of mid-spring for us. And so the fish are taken out of our special pen, they're brought into the factory, and we give it a corner in the factory. So we end up probably handling maybe 6 tonnes of fish, and because these fish have had these electronic tags in them, there's no way that the growers want them to go through as a commercial product. So we end up with 6 tonnes of salmon as giveaways, and to see the people descending on them is like watching a mob of seagulls. We have friends we never knew we had. But the factory it's a horrible place to work. It's noisy, you've got other activities going on, it stinks, it's fairly cold, but we just essentially have a production line where the fish get gutted, we weigh them. This is a keyboard which is logging to a computer. You can see the tag reader on the other side there. But we also measure some of the carcass quality traits. So this is a machine called the NIRS, and that's a machine that it's the. Do I need to explain it? I'll explain it very briefly. It's this wonderful black box, and you can measure the reflectance in the near infrared range. You can calibrate that reflectance to a set of calibrated samples, and you can get a good prediction of whatever you want to measure. So this is a salmon fillet, and we're measuring it for fat content and colour, or astaxanthin content. So we would have done chemical bioassays on probably 200 samples, and in the computer they've been calibrated against the reflectance that comes from this, and from our point of view you can get a very good relative measure of those properties. So the fourth part of our cycle of activity is the genetic evaluation, and this of course is a data intense process. It's a very time dependent process, so there's often only 2 or 3 weeks. Actually, it's less than that. There's often only a week between getting your measurement data in and the need to have selections and to have breeding decisions. So we've put a lot of effort into making a system, and if any of you have done data analysis, you probably won't be surprised when I say that about 80% of your time in a data analysis is getting your data together, and 20% is actually doing the analysis. So we've been working on systems that really make that 80% a mechanical process. And we've also been developing other bits of software I won't even talk about that, too complicated. So this is what's happened. So I said we started in 2004, so we've done enough breeding to know what we can change. So I think sort of the headlines of what we can say is that we've used these DNA pedigree markers in an applied program, and they work really well. It's just now just an operational tool. So we've looked at this disease, amoebic gill disease, and we found that it is under genetic control, and we do believe that we can make changes. And there's going to be a lot of slow steps, but what we're saying to the industry is that we think with 10 years of selection, they should be able to halve the number of treatments. So currently they're doing, let's say, 12 treatments in a grow-out cycle. We're saying you should be able to get that down to 6 with selective breeding. And we know all these other traits are under genetic control, so they'll also be changing. So growth rate will be changing, and this is the sort of percentage change that we're expecting. And this also shows, so I mentioned the primary traits and secondary traits. So the industry has said that they want us to put most of our effort here, so that's where you see the change happening. So this would be percent change per generation. A negative change is good, it's reducing the number of bathes. And these are the secondary traits, so these are the ones they're saying that they don't want to go any worse. So again, a negative change is a good change. It's just a small decrease. But they're not really going to make any groundbreaking economic benefits, but these we believe will. So challenges to the future. So AGD, the amoebic gill disease, is still an important trait, but because we do our performance test in the marine environment, and we can't take those performance tested fish back to our hatchery, Biosecurity, yes, we see opportunities for using genetic markers and for using SNPs to increase the rate of gain there. And we've done a sort of a cost-benefit case, and we believe there's a business case there as well. I haven't talked about this, but another need. Another challenge is to have a DNA marker for sex. I'll try and explain briefly. I talked about early maturation and how males have a much higher incidence of early maturation. So the commercial fish that are used are all females. So they use so the way they do that is that at hatching, so we're going way back into the cycle, they would take a sample of fish, they would feed them hormones, and so female fish develop testes. And maleness, gender is a male inherited trait. So when you cross what we call a neo-male or a sex-reverse female with a true female, then all the fish are female. But the logistics of that means that it's easy to make a mistake and have a true male when you think you've got a neo-male, so a sex marker would be really good. And the other thing the industry became increasingly concerned about is just the general robustness of fish. So fish die from handling. There's a lot of handling that goes on, and what they really want to know is, can we breed just a tougher fish, a fish that does better in sort of our environments, copes with the extremes. And that's it. Big thank you.
So moving the fish from marine to freshwater, what biosecurity specifically is the concern?
I'm not a fish disease person, so there's a whole range of there's diseases in the southeast of Tasmania which aren't in other parts of Tasmania. So I think they're rickettsia type things, or anyway, I don't know what the disease. I can't even remember what some of the diseases are. But the guys in the hatchery say that when they were transferring stock from the marine environment back to the hatchery, they said it was a hatchery manager's nightmare because they'd have fish that were in poor condition, and so they were getting poor egg quality, and poor egg quality means poor smolt, with a lot of unpredictability about it. So if you speak to a hatchery manager, he'll say he would much rather be in control of his brood stock anyway.
So genetically, the limitations you can't do within family selection?
That's exactly it, yeah.
What kind of a diversity of salmon, or what kind of diversity do you have inherent in this population? Been in New South Wales for a long time.
Yeah, that was the major concern. So when I said earlier there was a lot of indecision about should we do a new breeding program. So part of it was, well, is there enough diversity there to do it? So they did studies with DNA markers, and that said, yeah, this is okay. And then once we started doing the selective breeding, you do get different sort of measures of genetic diversity, and what we were seeing in that was really no different from what the things like the heritability or the amount of genetic variation was no different from what other salmon breeders have reported. So perhaps surprisingly, I don't think it's going to be a big issue.
So you haven't had to go to try to reinfuse the stocks with material?
And I mean, the nature of Australian quarantine people is that it would be a huge exercise. It would cost a lot of money, and no one really has the energy to do it.
I guess I could ask you about the disease issue. So the more resistant stocks, do they seem like they have less in the way of infections, or they just don't have that extreme sort of response to the infection when it exists?
It's a really good question, and it's something that we talk about a lot. We've never seen a fish that never gets a symptom. But we do see fish that have much lower levels of disease. So, and when you have those lower levels of disease, so they're producing sort of less mucus. They seem to have less acute symptoms, and does that answer?
So so it might be like a tolerance element to it, or a reduced severity of disease.
Oh, that's reality. So what we don't have at the moment is a way of measuring the parasite load. So we can see the signs, I was told to call them, on the gills, but we can't actually measure the number of parasites. So we do have someone who's working on a PCR method to be able to measure the parasite load, but we can't do that yet. So at the moment we just speculate whether it's tolerance or resistance, and we don't really know.
So do the fewer numbers of freshwater baths, are they determined by outbreaks in the whole population, or the severity of an outbreak in the population? In other words, now you're doing a certain number because everybody's getting sick, and so you have to treat them.
It's done cage by cage, and so when they see the symptoms, right, well, what they really see is that the least resistant fish are showing major symptoms. So then the whole pen gets treated. So we sometimes think, well, even if we took the tail out of that population, and so you didn't have the most susceptible fish in there, that maybe that would even just give them a slightly longer cycle. And we also wonder too about just this herd immunity thing. So when you see when they do this bathe, and after they do the bathe, you just see all this mucousy, cruddy stuff floats on the surface. They pull the pen and it just sort of floats around the farm. And you think, well, if there was less inoculum, maybe there's going to be less disease. And anecdotally, they say as the industry's scaled up, the level of disease has really gone up. And sometimes it gets to the point where they're really struggling to keep up. And they have fish dying. When they have fish dying, they're talking of losing millions of dollars.
Thank you, Peter, for this. Did you have a question?
Yeah, I'm going to talk about that. Yeah, I was okay, right? Fine. 7,500. What you basically sample 7,500. You sample that strategically from your tray, so you can guarantee family representation, or
so when we have trays, so they're families. So when we have these eyed eggs, we count out 500 eyed eggs, and they go into a communal tank. And after that, you'd have, I don't know what it is, 30,000 fish in there. Of those 30,000, we'd pull out 7.5, sometimes spend 10,000 to tag, and the other 20,000 or so, they're just waste, basically. They're rubbish. Because they're mixed sex, they don't want them commercially, and so, but that's just a random sample out of that.
How does the family proportions split out? You might get over-representation. Does that happen? What's the minimum number you would?
So I've looked at that, and I said, does this differ from what you'd get from a random sample? And basically it's the same. So the variation you get is no different from what you get in pulling coloured marbles out of a jar. Sometimes you get some families that have disappeared, but they're small numbers. Usually you can go back to your spawning notes and someone has written something like questionable eggs, or this milk looks strange, or something like that. Sometimes we'll see none of one family and twice as many as another family. I think that's the sampler's gone to sleep, taking 2 lots out of one tray and none out of the others. But it's the distribution's been surprisingly good.
How does that affect your block estimations?
I don't think it affects it at all. I think luck takes care of it.
So you have your mating designs that incorporate relatedness or links between families.
Yes.
Thank you, Peter.